Let's consider a linearly distributed load now. So it's given by the function Q naught times x over L. So L is the region over which the load is distributed. So it's distributed between the origin 0 and L. And Q naught has dimensions of force per unit length. And let's look at the replacement of this distributed load by an equivalent point force characterization. So first let's figure out what the total force is, and then we'll figure out where to place it. So the total force in this case is going to be the integral of Q dx integrated from 0 to L times Ey. That's the direction that the load is being applied. So we have 0 to L Q naught x over L dx Ey. So that's just the integral of x squared. So we get Q naught L squared over 2L Ey. So that's Q naught L over 2 Ey. So that gives us the total resultant force. So, and you'll notice that that's just simply 1/2 base times height. Right, so it's just the area underneath the distributed load gives you the total load, and the direction is the direction in which it's acting. Now, so I now know what the load is. It's Q naught L over 2 acting in the y direction, but what I don't know is where it acts. So let's just give that a symbol. I'll call that xc. So that's the distance to the point in which it acts. And what I want is the condition that the resultant moment about the point xc, I want that to be equal to 0. So that's my condition. So this is what I want. So let's go ahead and write out the relationship. So again, moment arm to the point xc times the load about a given point. So if you consider just some little region here dx at a distance x from the origin, this distance here is x minus xc, so that's my lever arm, and acting in this point here is a little bit of load, and that load is going to be q times dx. And so to get the total moment of the distributed load, I have to add it up over the entire region that it acts, so I integrate from 0 to L. And this will be acting about the z-axis if I take into account the directions of everything. So I'm going to get Q naught over L times L cubed over 3 minus xc L squared over 2 Ez when I do this calculation. And so this tells me then, but I want this to be equal to 0 here. So this gives me a formula to solve for xc. So I can go ahead and solve for xc to ensure that the quantity is equal to 0, and then I find that I get 3/2 L for the location of the load. So the final picture then becomes, if this is L, the load acts about here. It has magnitude Q naught L over 2, and this distance here is 2/3 L. So that's the equivalent system, equivalent point force system to that linearly distributed load.